Hello, and welcome to Empowered Learning. This particular lesson will be on functions. In particular, we want to talk about the basics of functions. We'll include the definition of a function and determining when a graph represents a function, as well as if we had a set of ordered pairs or a mapping, and to figure out if that is a function. So we start off with two different definitions of a function that pretty much are saying the same thing. It's just said in different ways. So our first definition is a function is a set of ordered pairs in which the first coordinate, which we're going to call the x value, corresponds to exactly one second component, which is going to be the y value. And so we can say first coordinate or first component interchangeably. Second definition says a function is a special type of relation between any two non-empty sets. And so the first set we're calling A and the second set we're calling B. And we want to make sure that we understand that the correspondence between two sets where both sets have at least one element in it, that's what we mean by a special relation between two non-empty sets. So we continue on with the definition such that each element in set A corresponds to or matches up with exactly one element in set B. So I'll read that one again. So a function is a special type of relation between any two non-empty sets, we're calling them A and B, such that each element in set A corresponds or matches up to exactly one element in set B. And when we say non-empty, we're just basically saying that the two sets have to have at least one element in it. Now, one of the things that I like to think of when I think of functions is that functions in mathematics basically gives us a representation or relationship in between two sets that are predictable. Okay? And so, for instance, the example that I have up here. So let's take a look at it right quick. So if you're a worker that works for either an hourly wage or a salary job, then the relationship between how much you get paid and how long you work is a function. And so we can look at this in a couple ways. So let's say I do a mapping here where I say you work 20 hours a week or 40 hours a week. And this is the number of hours. And then let's say whether you work 20 or 40 hours a week, you get paid $800. So this situation here would be like a salaried type of position. It doesn't matter how little or how much you work, you still get paid the same amount of money. Okay? Now the thing is that it's predictable. If we come and now make another mapping here, and let's say now we're doing 20 hours and now we say 40 hours, and let's just say this is $400 and this is $800, and we map 20 to 400 and 40 to 800, where this is hours amount you get paid. This is a situation where we have a function 2. And this is the case of an hourly person. And so this person is getting paid approximately $20 an hour. Okay? What we don't want is a situation like this. Well, let's say you work 20 hours a week, and let's say if you're an hourly worker, you have to decide on whether you want to be paid or you want to pay your employer. And in this situation, this would not be a function. Because the main thing you see here, you see that $20, we don't know whether you're going to get paid $400 or have to give your employer $400. And so the way I like to kind of remember this is by my key phrases. And simply put, we can have one person be in one place at the same time. We can have two people be in one place at the same time. So here is the first example, one person being in one place. This is the example of two people being in one place. But here we know we can't have one person trying to be in two different places at the same time. That's not predictable. And since it's not predictable, we can't call this relationship in between these two sets here a function. And so, in short, this is how we determine whether we have a function or not. If we were talking about a mapping, which is what I'm showing you here, and or a set of ordered pairs. So now what we want to do is look at some examples of some graphs and ordered pairs to see, can we identify whether we have a function or not based upon what we've just learned. Okay, so now what we want to do is look at some graphs and ordered pairs and mappings and see if we can determine whether they are functions or not. Before we do that, I want to reiterate that there are several different ways in mathematics that we express functions. And so one of these ways is via a mapping, which you've seen in the previous examples and during the introduction. So we also have algebraically, which is probably what most of us have been used to seeing as we first learned mathematics. We've also had a set of ordered pairs and a graph. And so this last one here, which is the function machine, this is just a sort of a graphical representation trying to show you what happens when we take a particular x value and we do all these things to it to eventually end up getting a function. Okay, so and I guess the way to think about it here is we're saying that the function acts upon any particular value x to give it a specific output. So as a quick example, let's say our function f here was 2x minus 3. So when we take x and put it into the machine, the first thing that we do to it is that we take whatever that x value is and we multiply it by 2, whatever it is. And then after that, we move it on. And then we say whatever this result is, which is going to be the x times 2 here, we're going to subtract 3 from that value. And then from that point, the machine spits out the result, and it's 2x minus 3. So that's sort of the idea behind the function machine. So now what we want to do is look and determine which of the following graphs are functions. Now, when we start to talk about graphs and being functions, we know that we can either have one x value pairing up with one other x value, x and y coordinates respectively, or we can have two or more x values pairing up with the same x value. But we can't have a situation where we have one x value trying to go to two or more different y values. So simply put, we can have this situation where one x value goes to a y value. We could have a situation where we have two x values going to the same y value. But what we can't have is a situation where we have one x value trying to go to two different y values. So we can't have that. How we test that graphically is by doing what's called the vertical line test. And so the vertical line test basically says that if we can draw a line, a vertical line that is, for any portion of the function, and it only intersects that function once, then what you have is a representation of a function. If you draw a vertical line anywhere in the function, and if even at one point the graph is intersected by that vertical line more than once, then it is not a function. Okay, so that's what the vertical line test says. So that's what we're going to use to be able to test to see whether what we're looking at is a function or not. So if we look at our first one here, if I start to draw some vertical lines, you'll see that no matter where I draw the vertical line, my vertical line is only intersecting the function once. So in this case, yes, this is a function. If we look for B, if we draw a vertical line through here, we see that the vertical line is intersecting the function at 2 places. So therefore, this is not a function. So this is again like our one x value trying to match up with two y values. In particular, whatever x value is here is trying to match up with the positive x, positive y here, negative y down there. Okay. For C, if we start to draw vertical lines, we see that here we don't have a problem. Here we don't have a problem. But right along here, we see we have open circle, closed circle. So if we draw a vertical line here, that's not a problem because we know that in this case, we only have really one point there, which is the closed circle that was here. But right here, though, as you see, we have two closed circles. So what that's communicating to us is that we have one x value trying to be paired with two y values. So in this case, this would not be a function. In contrast, for D, we see that we have open circle here, closed circle. So if we draw that line, that would only intersect once. Open circle here, closed circle, only once. And of course, all of these would just be once as well. So this would actually end up being a function. Moving on to E, now we're dealing with a set of ordered pairs. Again, what we see here is that every time that we had a graph that was not a function, we had one x value trying to pair up with two y values. So what that would look like as an ordered pair, let's say in this case, we would have a -2 trying to go with 5 and a -2 trying to be with, let's say, a -3 at the same time. And so we see that one x value pairs to two y values. So what we're looking for here in the set of ordered pairs is we want to see, do we have our x values being repeated? If we do, then we know that we don't have a function. If we don't, then we know that we do have a function. So here we have 2, -4, 15, and -2. So all these numbers are different, so therefore that makes E a function. If we look here for F, we have 20, 40, 60, 80. And so since all of these are different, this indeed represents a function. If we move on to this mapping now, we're doing the same thing. We want to make sure that we do not have a situation where one x value is trying to be matched up with two or more y values. So if we look here at -1, we see that matches up to 2, 0 matches up to 5, 1 matches up to 6, 5 matches up to 2, and 8 matches up to 7. So the only thing that may look a little alarming here is both -1 and 5 matching up to 2, but that's okay because two people can be in one place at the same time. However, in this case, we see here that 0 is trying to match up with both 5 and 8 at the same time, and that can't happen. So in this case, we know that this is not a function. And over here, since two people can be in one place at the same time, we know that this is a function. So this concludes our lesson on the basics of functions, and in particular, being able to identify whether a graph, a mapping, or an ordered set of ordered pairs is indeed a function or not.